Hey, what's up guys? In this video, what I want to do is kind of do a condensed version of everything you kind of need to know for exponential and logarithmic functions test. So a lot of times when, the day before my students would take a test, we would do something like this where I just kind of do like a quick little review, highlight some, important concepts that I want my students to understand, as well as kind of highlight some mistakes or some things to look out for. So we're just going to kind of run through all the topics that I would expect for you to know on a test for exponential and logarithmic functions. We'll do some specific examples and go through some specific problems. We'll do some specific examples, but also kind of talk broadly about a lot of the concepts to make sure you just kind of have a general idea. So if you have a test coming up or you just need a refresher on exponential and logarithmic functions, then this video was made for you. Now, the first thing I think that, we need to understand is what exactly is an exponential function. So in that case, what exactly is an exponential function? So when we have a function like f of x equals b to the x, okay? Now this is called an exponential function because again, what we notice here is we have a base, right? That's why we use the b, and then we have the x, which is going to be the exponent. Now, it's important when we're thinking about an exponential function, there's really kind of two different graphs we're going to be looking at. The first one is going to be a growth, and then the other one is going to be a decay. And it's really kind of important just to make sure we recognize what exactly these graphs look like, so therefore we can understand their behavior. So the growth function is basically going to be the graph as it's going from left to right is going to be increasing. Now there is a horizontal asymptote, which we'll talk about here in just a second. And this is going to happen whenever my b is going to be greater than 1. Now my decay function is going to look very similar to the growth function. However, when we're going from left to right, we're actually going to be declining here. And again, we're going to be approaching this horizontal asymptote. Now, there's one distinct point that we need to make sure we know, and again, this is very important when we're dealing with our graphing, is going to be the y-intercept. So the y-intercept for both these functions is going to be 0, 1. And when we want to eventually graph our functions, what we're simply going to do is just kind of shift our y-intercept using our transformations, or we'll shift using the asymptotes. Now, the decay functions are going to happen when I have a b, which is going to be greater than 0, but it's going to be less than 1. So typically that's going to be like a fraction. But again, don't get caught up with a mistake. Just because you see a fraction, then it has to be less than 1, because there are fractions that are greater than 1, like 5/3 or something like that. Remember, if you can take the fraction and write it as a mixed number, it's going to be larger than 1. So just a quick little example here, if I had like y equals a 3 to the 3/4 raised to the x, a lot of times what we'll say is this a decay function or is this a growth function? So remember, this is an exponential equation, right? Exponential. We are looking at the base. This 3 right here is just going to be a scale factor. That's actually going to be stretching the graph. So we don't care about this. The only thing that we care about is the 3/4. Since 3/4 is less than 1, but it is greater than 0, then this is an example of a decay function. So if I had these swapped, right? If, for instance, if I had y equals a 3/4, times a, let's say 3 to the x and wrote it like that, it doesn't really matter, but you can see now that my base of my exponent of my exponential equation is 3, and 3 is going to be larger than 1. So therefore, that would be an example of growth. So it's just very important when you're trying to identify if it's growth or decay to make sure you're looking at the b. Don't get distracted by that coefficient. Now, if we have a function, right, our parent graph is y equals b to the x, we need to know exactly what that graph looks like, right? We need to understand our transformations. And again, just to go ahead and graph this, and we'll assume that b is going to be larger than 1 here. So therefore, we can go ahead and draw this graph. It's going to be just like this, okay? And again, remember, we have this point here, 0, 1. Did I actually do that correctly? Yes, I did, okay. Now, the next thing we want to do is what about the transformations? What is happening to the graph when we multiply it by certain numbers? Like when we add or subtract it. Like for instance, what does this 3/4 do to this graph? What does the 3 do to that graph, right? And what about if we add and subtract numbers? So in our study of like transformations in other chapters, we should hopefully recognize that whatever we transform for one function is going to be the same for even our exponential and logarithmic functions. But we'll get the logs in just a second. So let's just focus on the exponential here. So I'm just going to use again some more letters. If I had f of x and we'll put an a in front here, b, and then we'll just do an x minus c plus d. Okay, so remember a is going to be your stretch and compression. So remember when a is going to be less than 1, that is going to be a reflection about the x-axis. Remember c is going to be your shift left and right, and d is going to be your shift up and down. Now just remember whatever the value is of d, like if d is positive, you go up, if d is negative, you go down. And just remember c, it's actually the opposite of c inside the function. So if I have like x minus c, that's gonna be actually shifting it to the right. And if it was x plus c, that'd actually be shifting it to the left. And again, we can practice a little bit more of this, like by using Desmos and kind of seeing how that relates. But exactly in this example, like since we're trying to, just review for the test, I don't want to go into the table because when you're taking a test, using a table is not always going to be the most efficient efficient way to graph a function. But if you get stuck, then I would definitely recommend, still kind of going back to those table stuff that we talked about in earlier lessons. But really, it's really important to recognize these and also the importance of B. Now, B is going to impact the graph as far as like how fast and slow it's going to be increasing. But the main thing is it doesn't really matter what B is. But the main thing, like if you're just trying to get a general idea of what the graph looks like, it doesn't really matter what if B is. Like if B is 2, if B is 3, like the general shape of the graph is going to be the same as long as B is greater than 1. Obviously, when B is less than 1, it's going to take a different curve, right? It's now going to be a decay function. So B is not going to be a general transformation. It is going to impact the graph, but it's actually not going to be transforming or shifting, the graph in that sense. So let's go and take a look at least some of the graphs. Let's go and see if we can transform them. Let's see if we can graph them. Let's go back and review the domain and range, the end behavior, as well as how to identify some points on the graph. Okay, so in this first example, the main thing we want to be able to do is just kind of understand our transformation. So whenever I see an exponential function, and if I'm trying to graph it, or if I'm trying to identify like the domain and a range, I still want to be able to identify the transformations. So the first thing I'm going to look at is since I'm subtracting 1 inside the function, right? It's inside the function because it's listed as an exponent. That's going to be a shift 1 unit to the right. And since I'm adding a 6 on the outside the function, right? It's not actually in the exponent. That's going to be shifted up 6. So my transformations are going to be shift right 1 and shift up 6. Okay, now, so if we want to sketch this graph, basically all we need to do is go ahead and take the parent graph and then just apply some transformations, right? So my parent graph here, it looks something like this. Now, so if I want to find the new transformations, again, what am I going to do? I'm just going to shift the graph over 1 unit to the right and then up 6 units. So I can take this point, shift it up 1, and then just go up 6 units. So 1, 2, 3, 4, 5, 6. So my new y-intercept is going to be right here. Now, again, you have to remember there's a horizontal asymptote going here. So in addition to the x-intercept being shifted up 6 units, also my horizontal asymptote needs to be shifted up 6 units. And again, this is not visible, but it's important because that's what the graph is approaching. So we're going to go up 1, 2, 3, 4, 5, 6. And you can say here, I'm going to have a horizontal asymptote right here. Now you can see this graph is going to take this kind of shape, right? So let's go ahead and move that down because it's kind of like in the way. But hopefully you kind of see what's exactly going on here. And actually, I'm going to just fix this. So then you can see the graph is going to be taking a shape of something like this, which is basically the exact same shape of my previous graph. It just got shifted again 1 unit to the right and then up, 6 units. Now, typically I do like to be able to say, like, what is this value? Like, how do you find the y-intercept? Like whenever you're graphing, it usually is helpful to have at least 2 points. And the easiest points to find is in addition to the old y-intercept, right? Just by applying your transformations, we can also go ahead and find the y-intercept. And again, the y-intercept is going to be when our x is equal to 0. So to do that, what if I want to find the y-intercept? I'm just going to say then x is going to equal to 0. So if I have f of 0 is equal to a 3 times 0 minus 1, and then that's what? Plus 6. All right, so let's see what this is going to be equal. So therefore, I have 3 to the negative 1, so it's going to be 3 to the negative 1 plus 6. So that's going to be a 1/3 plus 6. And then again, if I want to get these to be common denominator, just remember that's going to be over 1. So then I can multiply by 3 over 3. And then I'll have a 1/3 plus a 18/3, which equals a 19/3. Well, 19/3, let's see, that can be, if you want to rewrite that as a mixed number, you could. You could also verify this as a decimals, but I'm actually just going to leave this as a 19/3, which again is approximately what? 6 goes into 18, so it'd be 6 2/3. No, 6 1/3. Right? So just to kind of get an idea, like 6.33, you can kind of identify with there. And again, that like makes sense. If like you look at this, like my horizontal asymptote is at 6. So therefore 0.33 would kind of make sense for my asymptote, right? So I'll just do a 0, 19/3 for my y-intercept. The other thing, so now let's go and take a look at the domain and range. I want you to understand that just because I took this graph, I shifted it, to the right 1 unit. But again, did that change my domain? No. Did that change my range? No. So if you take this graph and just shift it right horizontally, that's actually not changing the domain and range, because the only thing that's restricted on my parent graph is the range, right? The range cannot be below a negative number. It cannot be below this horizontal asymptote. So what happens is when I shift this now graph up 6 units, well, the range has now changed from 6 to infinity. So let's go and identify the domain here. So the domain is unchanged. It's negative infinity to infinity. It's all real numbers. And the range, though, is now going to be to its lowest value, which is at 6, which is my asymptote, and to infinity. Let's actually go ahead and move this information up here. Put over here so then everything is by next to each other. There we go. And then we'll just go ahead and call this the y-intercept. So my y-intercept, right, is going to be what I say, 0, comma 19 over 3. Okay, so my domain and range, you can see now the graph is only going down as low as 6 here, and then it's going up to infinity, whereas the graph going from left to right is expanding from negative infinity to positive infinity. And there you go, guys. That's basically what I want you to be able to know for the graph, is to be able to identify the transformations, identify the y-intercept, and identify the domain and range. Okay, so let's go and take a look at another example so we can go ahead and practice. And you can see in this example, we do not have the same type of function, right? Because this has a base that is less than 1. So this is going to be a decay function. So again, remember, like when we're looking into graphing it, I want to be able to identify my transformations based on the parent graph. So the parent graph in this case is actually not going to be a growth function, right? It's actually going to be decay. So it's important that here is my decay function. It's going to look something like this. And again, this is just the parent graph, right? So let's go and look at the transformations that we have and then kind of identify, well, how is that going to change this graph? So one of the big important things here is we have this 2. Now this 2 is positive, so that's good. But it's also going to be a vertical stretch of the graph, which is actually going to change the y-intercept. So be very careful when you recognize this. And again, we'll see how that works by just using a simple point to demonstrate that. So again, we're going to have a vertical stretch of 2. Since I'm adding a 5 inside the function, right, it's as an exponent, that's going to be shifting it 5 units to the left. And then I'm shifting it up 1 unit. So up 1 unit. Okay, so now if I just wanted to go ahead and simply graph this, again, what I can do is I can simply, now again, we're not trying to be exact here, right? But what I want to do is let's basically take this graph here, and I'm just going to shift it 5 units to the left and then up 1 unit. Now to graph this, we can basically apply the transformations, but again, we don't want to use this point here because this 2 is actually impacting it. So the way I can explain this is, let's just take a look at a quick little function. Let's say I have g of x times 2 raised to the 1/2 x, right? So that graph looks something like this, right? But again, watch out. When I plug in x of 0 or g of 0, right? Look what we have. We're going to get 1/2 raised to the 0 power, which is now going to give me a 2 times 1, right? So what I want you to understand here is that's going to be equal to 2. So g of 0 is actually equal to 2. So what happens is whatever my scalar is, that's actually going to tell me what my new y-intercept is. So in this case, I don't want to shift 0, 1. I actually want to shift the point 0, 2. And so what I'm going to do is I'm going to go left 5 units, 1, 2, 3, 4, 5, and then up 1 more unit. So I have 0, 2, I'm going to go over 5 and up 1. So this new point that I have on the graph is going to be at a -5, 3. Right? So it's important to kind of recognize that. We also have our our horizontal asymptote, which is just being shifted up 1. So therefore that's going to look like that. And then we can also find the y-intercept. Now again, to find the y-intercept, we know that x has to equal 0. So we're going to go ahead and do this in the exact same case here. So what I'll have here is 2 times a 1/2 raised to the 0 plus 5 plus 1. 0 plus 5 is just going to be a 5. So therefore I have a 2 raised to the 1/2 to the 5th power plus 1. Now 1/2 to the 5th power is going to be 1 to the 5th, which is 1, and then 2 to the 5th, which is going to be a 32. And now what I'm simply going to do is I can just multiply this 2 over 1 times 1 over 32 and then add it to 1. But again, I want this 1 to have the same denominator as 32. So what I'm going to do is I'm going to rewrite 1 as 32 over 32. Okay, and now you guys can see that my y-intercept is going to be a 34 over 32. So just a little bit over 1, which again, kind of makes sense, right? Because I have a horizontal asymptote here at 1. So my y-intercept is going to be 0, a 34 over 32, which again, dividing by 2 on the top and bottom could be reduced as a 17 over 16. And again, that's going to be like that little point right there, 0, a 17 over a 16. Okay, and then the graph we know is going to have that kind of pattern. Now it's also important it's approaching the asymptote, right? It's not crossing. So it's important also for us to recognize our domain and range. Now notice in this example, my domain, again, by these transformations did not change, right? It's still going to be -infinity to infinity. And my range is basically still the same, but now the lowest value is going to be a +1. So my domain here is going to be the same. So -infinity to infinity. And my range here is going to be from a 1, to infinity. The only other time that the range could change is if we have a reflection about the x-axis. But I want you to understand, since the domain is all real numbers, it doesn't matter what transformation I do. Shift, left, right, up, down, reflect x, reflect y. It doesn't really matter. It's not going to impact the domain. Now let's just go and do a quick little review of our logarithmic function. So again, when we're dealing with logs, again, we need to know what our function is. We need to know our general function. So log, we have like log of x, or also we could both be dealing with ln of x. And it's important to recognize that for both these graphs, it's going to take on the shape just like we had for the exponential function, which is actually the inverse of the function. So if you remember the exponential function of y equals b to the x, and again, this is helpful like whenever you if you do forget it, y equals b to the x, that's just the equation form. If you wrote it like this, what I want you to understand here is this is just the inverse, right? So what we have here is this point is 1, 0. It's just swapped. So therefore the graph is going to, take this kind of shape here. And then again, if we have a horizontal asymptote, and this one, well now for the logarithmic function, it's going to be here. Now, again, just kind of like we had for the exponential function we have the base b, it doesn't really matter what the base is. It could be 10, it could be 5, or it could even be e. The shape of the graph or the general shape of the graph is going to still be exactly the same. Obviously, that is going to increase and decrease. That's going to change as we're graphing it, but the general idea of it's going to be the same. Now, we're also going to have our transformations, just like our exponential. So I can say, f of x is equal to an a log of b of x minus c plus d. Again, a is going to be our vertical stretch or compression. And when a is less than 0, it's going to be a reflection about the x-axis. And then c and d are going to be our vertical shift. So it's just important to recognize how those are going to be impacting our graph. So let's just go and take a look at, a quick little example of, how to graph them and then how that's going to impact the domain and the range, as well as how that's going to impact the graph. So let's go and take a look now at just an example to see how we can identify the domain and the range. Okay, so in this example, we have ln times x minus 3 plus 1. So again, it's very important to understand the difference here. The 3 is inside the function, right? That's our c, so that's going to be our horizontal shift. Whereas the 1 is outside the function, so that's going to be our vertical shift. So it's very important to know the difference because when it's inside, it's horizontal. Outside, it's going to be vertical. Now, there's no other stretch or compression or reflection that's going on here. So in this case, what we can look at is, let's just go ahead and sketch the parent graph. Y equals ln of x, and that's going to look something like this, right? And now again, we know this point here is at 1, 0. Right? So now let's just apply the transformations. Let's shift this graph 3 units to the right and then up 1 unit. So we can go 1, 2, 3, and then let's just go up 1 unit. And voila, there's our new point. But remember, we also have a vertical asymptote. So if we're shifting left or right, that vertical asymptote also has to be shifted. So now I'm going to go over 3 units, 1, 2, 3, and I'm going to draw a nice little vertical asymptote right here. And then now I can just go ahead and sketch my graph. Now, if you remember from exponential equations, right, my domain was unlimited, right? It could keep on going to the left, keep on going to the right. The range, though, was limited to only positive numbers. Now, look at over here. When you look at the domain and range of this parent function, the domain is now restricted, right? It's only restricted to positive values, whereas my range is not restricted. It looks like the graph is going to continue going down and continue going up. So here, let's just look at this new restriction. It was for only positive numbers, but now the vertical asymptote got shifted over 3 units. So my domain in this case is going to be from 3 to infinity. And again, I'm going to use an open parenthesis because it's at an asymptote. It's actually never going to achieve 3. And my range is going to be all real numbers. All right, let's go and take a look at one more example because I do want to address the transformations, which we haven't really talked so much about. So I want to be able to make sure we can address those as well. Okay, so in this example, we have a lot of negatives going on here. But again, it goes back to that inside and outside identification. I want you to recognize that this is a negative and this is a negative both on the outside. That means they're going to be vertical transformations. Now, this is basically a -1 being multiplied by the log. Whenever you have multiplication by negative, that's going to be reflection. And again, if it's vertical, that means it needs to be reflected about the x-axis. So therefore, my first transformation is going to be reflect the x-axis. Now here, I'm subtracting a 1 on the outside of the function. So therefore, that's going to be a vertical shift down 1. Now, the last point we have here is we have a couple things. What we have here is we have this -2x. Well, what exactly is this -2 doing, right? I talked about this in more graphing a logarithmic equation. So it is important for you to recognize what happens when we do a b. Now we need to understand what is happening on the inside. Now remember, whatever's on the inside is kind of like the opposite of what's going on the outside, right? So if the multiplying by negative on the outside is reflect the x-axis, well, what do you think multiplying by negative on the inside is? Reflecting the y-axis. If multiplying by 2 on the outside is going to be a vertical stretch of 2, well, then multiplying on the inside is going to be a horizontal compression of 2. So that's exactly what's happening to the graph. It's being horizontally compressed and it's being reflected about the y-axis. Okay, so now let's go and see how are we going to graph this and then identify the domain and range. And again, we got to start out with what the function, the parent graph is going to look like. So that's just going to be a, f of x equals a log of x. And again, that graph is going to look something like this. It's going to have a y-intercept here at 1, 0, and voila. All right. And again, remember we have a vertical asymptote going on right there. So let's see what happens. Now, the first thing we're going to want to do is actually apply the restrictions from the inside first. So the first thing I'm going to do is I'm going to reflect this about the y-axis. So reflecting this about the y-axis, I'm going to now produce this graph, right? So that's going to be a, let's just say the negative 2x is being applied there. And then it's saying, well, in addition to that, now you need to reflect this about the x-axis. So now the graph is going to be looking like this, right? So now it's a negative log of 2x. And let's just call that a log of 2x. And then last but not least is we need to shift it down 1, right? So now the graph is being shifted down 1. So it's going to look something like that. Now, it's important to understand that the asymptote did not move, right? Because all it did was I reflected the graph. And again, let's just kind of look at this one more time here from these more transformations. So the original graph looks like this, right? Now this graph is going to be shifted, reflected about the y-axis is here. Then the shifted about the x-axis didn't change anything. And then it just got shifted down 1. So graph looks something like that. And again, still has my horizontal asymptote. Now what we want to do is, well, let's make sure we can identify the domain and range, right? So my domain is going to be all negative numbers to 0. So negative infinity to 0. And my range is going to be, again, unrestricted. So negative infinity to infinity. There you go. And hopefully now we have a good foundation of the relationship between the exponential function and the logarithmic functions, especially looking at them from a graphical approach, because remember, they're inverses of each other. They undo each other. You can see how to go from one to the other. That's very important because for the rest of the problems in this chapter, we want to make sure that we can relate our logarithmic functions to our exponential and our exponential to our logarithmic. And again, that just kind of starts with like, well, how do we understand then an exponential equation in logarithmic form? So again, it's just really important to recognize, like if I had 8 squared, we know that answer is going to be 64, right? But we can also understand this. This is exponential, right? We have an exponent. We can also understand this in logarithmic form. And the way I like to explain this the best with the students is just remember base, 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 base. You got to remember this is your base, right? And that is going to be your exponent. So when you have a logarithm, logarithms also have a base. So the base is always going to remain the same. Now that we have the base, again, we want to explain this equation, but in logarithm form. So this equation says 8 raised to the second power equals 64, which we know is true. In this example, if we didn't know what the exponent was and we wanted to solve for it, we could say 8 raised to what power equals 64? Well, that answer is going to be 2. So in a logarithmic equation, what we're doing is we're looking for the exponent. So that is going to be the answer we're going to be trying to solve. So again, just make sure you can kind of apply and understand the relationships. A lot of times, just remember bases are the same. Exponent is what you're trying to solve for in logarithmic, and the value is what you're trying to solve in exponential, which is what we call the argument of the logarithm. Now, this is really helpful in not only solving, but also just evaluating logarithms. So let's just work through a couple examples to make sure we really have a good understanding of evaluating logarithms. Okay, so in these examples, again, what we're trying to do is we're trying to find the value of the logarithm. And again, a lot of students will get confused on these because logarithms can just be tricky. So if you do get confused, remember, this is an argument, right? So it's going to be equal to a value, right? And again, if you can remember that it's equal to the value, and what are you trying to find for the logarithm? You're trying to find the value of the exponent. So there, basically, this can be rewritten as 9 raised to what power equals 81. And that's how we read a logarithm, right? We say log base 9 of 81. But really what that means is 9 raised to what power equals 81. Now, hopefully in this example, this one's easy enough for us to identify that x is equal to 2. Right? So we can just say that the log base 9 of 81 is equal to 2. Now, not always is the case. Is it always going to be, that easy? So in this case, we have 81 raised to what number is 9. Now, hopefully with some experience, you'll be able to get this one. But again, if you get stuck, just set it equal to x, right? So we can say 81 raised to x equals 9. And remember solving exponential equations, which we're going to get to here in just a second, we can rewrite 81 as a 9 squared equals 9. And therefore we can say 2x is equal to a 1. And then you can divide by 2, x equals a 1/2. In this example, again, we kind of have the same thing, right? Set it equal to x. So 9 raised to x equals a 1/9. Well, again, 1/9 we can rewrite as a 9 to the negative first power. So 9 to the x equals 9 to the negative first. So x equals a -1. Now in this example, hopefully this one you can really kind of quickly see that 9 raised to what power equals 1? Well, again, any number raised to the 0 power is always going to go 1. So we can find this answer just to be 0. Now again, I'm including x in this case. You do want to just set the value equal to 0. Like I am adding in an x just for explanation purposes. In these examples, now again, when you have fractions, again, this is where a lot of times students will get confused. So 1/9, raised to the x equals 81. And again, just rewrite it. So 9 to the negative first power, right, raised to the x equals a 9 squared. Well, again, here, then we have a negative x equals 2. So x equals a -2. So that's the value of that function. 9 raised to what power equals 9? That one's easy. That's 1. 9 raised to what power equals 0? That's interesting. Think about it. 9 raised to what number is equal to 0? Now again, remember, what is an exponent? An exponent means repeated multiplication, right? 9 raised to the 0 power is 1. So is it possible in our real number system to raise 9 to a number to get 0? And not in our real number system. So that is going to be, it does not exist. And the same thing here. Like 9 raised to what number equals a -9? Well, it doesn't matter how many times I multiply a 9 by a positive or a negative number, it's never going to make a negative value. Because remember, 9 to the negative first power, that equals a 1/9. So again, this is another example of a value that does not exist. So whenever you get stuck when you're evaluating your logarithmic equations, just remember to kind of think of them in exponential form to be able to better understand them. So now that we've practiced a little bit more with logs, it's time to kind of get into the properties of logarithms that we need to make sure we know. Okay, so our three main properties is going to be the product, the quotient, and the power. And again, a quick way, like a quick simulation for these is remember the rules of exponents. Basically going to be kind of like the exact same thing, right? And you can see that relationship that we talked about when we were first introducing these. Then the main thing we have here is whenever I have a log of a base, whatever the base is, when I have a product inside that argument, I can rewrite that as two additional logarithms. But remember, these rules go the other way as well. If I have the logarithm plus another logarithm, as long as they have the same base, I can multiply the arguments. And again, that kind of also works with radicals. If you remember like the rules of radicals, we have the same kind of idea. For the quotient, again, when I have a log base b of m or n, remember we can subtract them. And again, as long as we are subtracting two logarithms with the same base, we can rewrite them as a quotient. And then the power rule, whenever we have a logarithm with the argument raised to a power, we can rewrite that in front as multiplication. So our properties of logarithms are really helpful for us to be able to condense and expand expressions, which can be helpful for us for just simplifying expressions or solve an equation. Let's just go and take a look at two examples of at least condensing as well as expanding. All right, so in this example, remember whenever we have parentheses, the main thing we're going to want to do is work inside those parentheses first, right? Go back to the order of operations. So in this case, what I recognize is you always want to apply the power rule if you can first. Now this is an argument here, ln of 4x, but I can go ahead and rewrite that as up front here as a power. So 3 ln of 6 minus, let's rewrite this as the ln of 4x raised to the 3/2 plus a ln of 5. And again, that's in the argument. But now you notice that ln both have a base e. I can rewrite these as the product. Now again, this is going to be raised to a power, which again is going to be the same thing as the square root of 4x cubed. So therefore, I can go ahead and rewrite that as a radical. So therefore, I have a 3 ln of 6. Then I'll just go ahead and rearrange this as a 5 times in front. So therefore, this will be an ln here of a 5. And then this is going to be the square root of a 4x. And that's going to be a quantity to the third power. Okay, so now I recognize I forgot to do the power rule here. So that can be written as a ln of 6 cubed, right? Which is going to be a 216. So ln of 216 minus here a ln of 5 times the square root of 4x cubed. Okay, now again, notice that we have both ln's, right? They're both at, base e. So now we can see we're subtracting. So therefore, that's going to be looking for the difference here. So then my final condensed version here is going to be a 216 divided by a 5 square root of 4x, raised to the third power. Okay, and you can see that what we did is when we're condensing, we condensed them all the way down to one single logarithm. Now in the second example, what we have is we have one single logarithm. What we now want to be able to do is expand this to multiple logarithms. So the first thing we're going to do is I'm going to rewrite this radical as a rational power. Just like here, how we wrote the rational power as a radical, now we're just going to kind of go in the reverse operation. So since everything is under that quantity of the radical, I want to be able to write that as a rational power. So what I'll do is say log. Okay, and now notice the power rule. I can take all my powers and rewrite them down in front. And now what you recognize is each of these values inside of my argument is separated by multiplication. Now again, this 1/2 is still multiplying by this whole logarithm. But what I want you to be able to see is now I can separate each of these into their own logarithm. And I just want to make sure I'm using parentheses again to represent that all of those functions are going to be multiplied by 1/2. Okay, so there you go, ladies and gentlemen. You can see now by expanding, I had to rewrite the example using multiple logarithms. But the process is the same. When you're condensing, you're trying to go down to one example, whereas expanding, we're trying to expand them using multiple. And we're using the same properties of logarithms, but just in a different order. Now, we already did a quick little review of solving exponential equations when we were evaluating logarithms, but it's also important when we have a little bit more complicated examples. So, just remember, like if I have 3 squared is equal to, 3 to the x, like how do we solve this? Well, again, we don't really need to do much, right? Whenever our bases are the same, we know that the powers have to be the same as well. So x is going to equal to 2. So there's a couple different ways we can use this. So we always want to first look to see if we can solve using what we call the 1-to-1 property. So in this first example, you can see that my bases are not the same, but can I rewrite these as the same base? And one thing I recognize is 9 and 27 are both powers of 3. So I can rewrite 9 as going to be a 3 squared, right? Still raised to the w minus 8. And then 1/27, I can rewrite as a -3, right? Because remember, negative, you're just going to reciprocate. And again, that's still going to be written to the 2w. Now, remember the power rule of exponents. Whenever you take an exponent, raise it to another exponent, you're actually multiplying. And again, since my bases are the same, I can apply this 1-to-1 property. So therefore, this is going to be 2 times a w minus 8 is equal to a -3 times a 2w. Okay, now I can just go ahead and apply distributive property. Notice how I inserted the parentheses here? That's very important. So therefore I have a 2w minus a 16 equals a -6w. Now I just want to get my variables to the exact same side. So I'll add a 6w to both sides and I get a 8w minus 16 equals 0. Add a 16 to the other side. So 8w equals 16, divide by 8, w equals a 2. What about when you only have one exponent? Right? And you can't use the 1-to-1 property. So in this example, what we're going to want to now do is use what we call our inverse operations. We want to isolate our exponential equation. So in this example, what I'll do is I'll add 11 to both sides and I'll have a 2 times a 3 raised to the 4y is going to equal what? A 72. Then I'll divide by 2 on both sides and I get a 3 to the 4y is equal to a 36. Now you might be saying, well, how do I solve for this? Now again, this goes back to our solving our logarithmic equations, right? I don't know how I can solve for y, but again, when we want to solve for exponent, what do? We look for our logarithmic equations. So what I'm going to do is I'm going to convert this to a logarithm. And again, remember the base is the same. So I'll have a log base 3. And again, of 36 is now going to equal to a 4y. So then I'll divide by 4 on both sides. And I can say y is equal to a 1/4 log of 3, 36. Now, how are you going to figure out the 3 raised to what power equals 36? Because it's not going to be an integer. So again, remember when we have a logarithm of different bases, we can use what we call the change of base formula. So what we'll do is I'll rewrite this as a 1/4, which again is the same thing as dividing by 4, as a log base 10 or base e, or any base really, of 36 over a log of 3. Now that's what I'm going to plug into my calculator and let's go and see what our answer is. And just using a little rounding to my nearest thousands, I get 1.305. Now in this last example, for some reason, students just get confused as heck when we have e. It's really going to be the last same example that we did in the previous one. All you're going to do is if there's only one exponent is, isolate your exponent. So in this case, I will have a e raised to the a plus 1 is equal to a 5. Now again, I can't undo this a plus 1. I have to get it outside of my exponent before I can actually solve for it. Now in this example, we rewrote this as a logarithm, which you could also do in this case. I can also just take the logarithm of both sides with the same base. So therefore I could have ln of e to the a plus 1 equals the ln of 5. And again, that's going to be base e. Now again, remember the rules of exponents say as long as it's the same base of the argument, then that's just going to equal my power, which is a plus 1 equals a ln to the 5. Then I'll subtract a 1 on both sides. And again, you're going to want to use your calculator here. So therefore, this is going to be a ln of 5 minus 1, which again, using my calculator is going to be approximately 0.609. Now for solving logarithmic equations, we're going to want to use the same process. We're going to look into using inverse operations as well as the 1-to-1 property, but we also have to be very careful to check our solution because we can also have an examples of extraneous solutions. And again, remember extraneous solutions is just when we have a solution for a simplified version, but not the original equation. Now in this first example, what I want you to recognize is I have a logarithm equal to a logarithm. And whenever you have a log equal to a log, the best, easiest, fastest thing to do is just like we did for exponents, is set the arguments equal to each other. So now I can just rewrite this as an x squared minus x equals a 6x plus 18. So guess what? We were doing a logarithmic equation and we quickly just now converted this to a quadratic. Now when solving quadratics, remember we want to get everything to the same side and set it equal to 0. So to do that, I'll subtract a 6x on both sides and subtract an 18 on both sides. Therefore, now I'll get a x squared minus 7x minus 18 equals 0. And now I can just go ahead and factor this. You know, what two numbers multiply to give me negative 18, but then add to give me a negative 7. So since this is a negative, one's positive and one's negative, my 9 is going to have to be negative, and then plus 2 is going to be a negative 7 here. That's what I'm getting. So I'm going to say an x minus 9 times an x plus 2 is equal to 0. Now I can just use the zero product property, set them both equal to 0. And therefore, x equals 9 and x equals negative 2. Now, again, remember what I said. We got to make sure we're plugging these back in to make sure that these are going to work. So basically, since the log is equal to log, we just want to make sure the arguments are going to work on both sides. So this would be 9 squared, which would be 81, minus another 9, which is going to be a 72. So we want to make sure this is going to give us a 72. 9 times 6 is 54, plus 18, which again is going to be a 72. What about negative 2? So negative 2 squared is 4, minus a negative 2 is going to be 6. That works. Negative 2 times 6 is going to be negative 12, plus 18 is 6. So both of these solutions are going to work. Now in this example, one of the biggest mistakes students make is they see this and they're like, oh, let's just go ahead and cancel out the logs. And no, we don't want to do that in this example. You can only do that when you have a logarithm equal to another logarithm. So what we're going to want to do is use our rules of logarithms to simplify this. So I see there's a 2 in front, so I'm going to bring that up as a power. And then these, I can condense these using the quotient rule. So now I have an ln of y plus 5 quantity squared equals ln of 20 over 5, right? Which actually can be reduced down to a 4. However, notice I have a logarithm equal to a logarithm. It doesn't matter if it's a natural log or not, right? So I can now just say y plus 5 quantity squared equals 4. Now let's go ahead and simplify this, right? So y plus 5 quantity squared is going to be a y squared plus 10 y plus 25 equals 4. And again, this is another quadratic. So again, we're going to want to set this equal to 0. So I'll subtract it over. So I have a y squared plus 10y is plus a 21 equals 0. Now this factored form is going to be, well, two numbers multiply to give you 21, add to give you 10. Well, 7 and 3, right? Y plus 7 times y plus 3, they both have to be positive, equals 0. And then I can say y plus 7 equals 0, and y plus 3 equals 0. Y equals negative 7, y equals negative 3. Okay, so now we got to go back and check our solutions. We don't want to check this solution. We already know this is true. We want to make sure these solutions are going to satisfy the original equation. And already I can see that negative 7 does not work, because look what happens. When you take negative 7, you plug it into the equation. Negative 7 plus 5 is a negative 2. You cannot take the logarithm of it with a negative argument. So therefore, this is going to be what we call an extraneous solutions. Now let's just go and take a negative 3 here, just real quick. So negative 3 plus 5 is a 2, and then 2 raised to the second power would be 4, right? And we know that's going to be ln of 4 equals ln of 4. So therefore, this solution is going to work. Now in this last example, you can see that we only have one logarithmic equation. We're not going to look into using the one-to-one property. What we are going to want to do though is isolate our logarithm. So we're going to do that now by adding a 14 and dividing by 2 on both sides. Now what we're trying to do is we're trying to solve for m, which is inside of the argument. So there's a couple of ways we can do this. What we can simply do is just rewrite this in exponential form, right? If I rewrite this in exponential form, I'm going to have a 2 raised to the 7th power equals a 9m plus 2. Now I just need to know what 2 to the 7th power is, which is going to be 128 equals 9m plus 2. And then I'll subtract a 2 on both sides. 126 equals a 9m. Divide by 9 on both sides, and m is going to equal a 14. Again, we want to make sure this is not going to make our argument negative, which indeed it does not, so we are good to go. Another way you could also look at this is also using your rules of exponents. When you have the log base 2 of a 9m plus 2 equals 7, you can also raise both sides with a base 2. So then that would just leave you a 2m plus 2 equals a 2 to the 7th, which is the exact same thing we achieved there. It really just kind of depends on how familiar you are with the rules of your logarithms when you're taking the test. And the next thing I just want to cover is going to be simple and compound interest. It's just very important to make sure we recognize these formulas and maybe actually even remember these or practice them, at least inputting some different values. So when we're dealing with simple interest, remember that's just going to be the total amount of interest based on the time and the interest rate off of your principal. The interest you earn is not going to be growing on itself. itself. If we want to find the simple interest, we're just going to take our principal times 1 plus r and then raise it to t, where t represents the number of years. Now, compound interest is where you earn amount of interest, but then every single compounding period, typically daily, monthly, yearly, it's going to grow. It's going to take that amount and compute the new interest based on what you previously earned. So when we want to find compound interest, we have a equals p times 1 plus r divided by n. So you're going to take the number of compounding periods, you're going to take your interest rate divided by the number of compound periods, and then you're going to raise it to an n times t. So this n is going to be very important. Now let's just take a look at two different examples. Let's say you invest $5,000. So we're going to say p equals, $5,000. And let's just take a look at two things. Now, your first way you could do it is, let's say R equals a 2.3%. Now, let's just say this is like in a bond program, like in the government, right? And they're going to say, we're going to give you this interest rate. And let's say T is going to equal 15 years. All right. Because you don't want to lose your money. And this is it's tied to government. It's going to be a very safe bet. So they say, all right, in 15 years at 2.3%, basically there's zero chance that you're going to lose your money and you're going to invest $5,000. How much money will you have at the end of 15 years? So it's very important when you're importing this to not use 2.3%, but use 0.023. So now all I'm simply going to do is I'm going to go ahead and simplify that to a 5,000 times 1.023 and raise it to the 15th power. Now I'm going to raise this to the 15th power first and then multiply by 5,000. And when I do that, I have $7,032.42, which again is not too bad, right? I mean, if you didn't do anything, if you didn't have to do anything, you didn't have to work for that, you kind of made an extra $2,000. Pretty good. But what about if we have something where we have an n, where it's going to be compounded? Even though we calculate the stock market as a compounded on a yearly front, let's just look at this and pretend that we get our gains every single month and we're going to have things compounded on a monthly term. So let's say you take the same amount of money. Now again, the stock market, you have much more risk. Companies could go bankrupt and you could lose all of your money. However, because of that risk, let's say you're going to earn a much higher percentage. Let's say you're going to earn 8.1%. So you're going to take the same amount of money, $5,000. Let's have the rate is going to be an 8.1%. We're still going to use 15 years, but now we're going to have our compounded period is going to be monthly. So therefore per year, that's going to be 12. Now let's just go and plug in these values into our formula. Now we'll just go ahead and simplify this. So A equals, a 5,000. And then we'll have a 0.081 divided by 12 plus 1, which is going to be a 1.00675, and that's going to be raised to the 180th power. So I'm going to take this, raise it to the 180th power, and then I'm going to multiply that by 5,000. And just by doing that, ladies and gentlemen, I have $16,782.82. So that's a huge difference, right? Same year, compounding period is a little bit different, right? But even if you did yearly, it would still be a large value. But the interest rate changed a lot, and also that this value was compounding. You actually not just earned $2,000, you actually tripled your money in 15 years. Pretty cool. So just remember, whenever you're doing the compound or simple interest, make sure you understand if it is simple or if it is compounding. And again, compound, you're going to have a compounding period. And again, basically it's just going to be plugging them in and then simplifying. Hopefully this video was helpful for you preparing for or reviewing exponential and logarithmic equations. If you want more examples, then check out the playlist and resources I have down below. Otherwise, I look forward to seeing you guys on the next video. Cheers.